NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial video. Today, we'll solve a problem involving powers of binomial expressions. Let's look at our example. We need to expand the expression a minus 3 raised to the power of 4. Our first step is to rewrite this expression as a square of a square. We'll use the property that a power to a power means we multiply the exponents. So, a to the power of 4 can be written as a squared. This means we can rewrite a minus 3 to the power of 4 as a minus 3 squared, and then that whole expression is squared. For our second step, we need to expand a minus 3 squared. We'll use the binomial square formula, which states that a minus b squared equals a squared minus 2a b plus b squared. So a minus 3 squared is equal to a squared minus 2 times a times 3 plus 3 squared. That simplifies to a squared minus 6 a plus 9. Now for step 3, we need to square the result we just found. Since we have a trinomial, we'll use the formula for squaring a sum of 3 terms, which states that the square of x plus y plus z equals x squared plus y squared plus z squared plus 2x, y plus 2x, z plus 2yz. For our expression, we'll substitute x with a squared, y with negative 6a, and z with 9. Let's compute the square of this trinomial using our formula. We have a squared minus 6 a plus 9 squared. According to our formula, we'll first find the square of each term. A squared, which is a to the 4th power, plus negative 6 a squared, which is 36 a squared, plus 9 squared, which is 81. Now, we need to add the cross terms. We have 2 times a squared times negative 6a, which is negative 12 a cubed, plus 2 times a squared times 9, which is 18 a squared, plus 2 times negative 6 a times 9, which is negative 108a. Now, let's combine all the terms to get our final expansion. We have a to the 4th power minus 12 a cubed plus 36, a squared plus 18, a squared minus 108 a plus 81. We can further simplify by combining like terms. 36 a squared plus 18 a squared gives us 54 a squared. So our final expansion is a to the 4th power minus 12 a cubed plus 54 a squared minus 108 a plus 81. To summarize what we've learned, we expanded a power of a binomial expression by first rewriting it as a square of a square, then using the binomial square formula to expand the inner expression, and finally using the trinomial square formula to expand the outer square. This method is useful for expanding higher powers of binomial expressions when we can break them down into smaller, more manageable steps. Welcome to this math tutorial. Today, we're going to learn about completing perfect square patterns. We'll solve problems where we need to find missing terms to make expressions equal to perfect squares. Let's look at our first example. We have the expression. Our task is to determine what these missing terms should be so that the entire expression equals a perfect square. To solve this problem, we need to recognize that we're trying to form a perfect square pattern. Remember, a perfect square has the form, open parenthesis, a plus b plus c close parenthesis squared. When we expand a perfect square like a plus b plus c squared, we get a squared plus b squared plus c squared plus 2, ab plus 2, ac plus 2bc. Looking at our problem, we need to identify what a b and c might be. Let's analyze what we already have in our expression. We have a squared as our first term, which suggests that a equals a. We also have 9b squared, which suggests that b equals 3b. And we have 6 at the end, which should be a cross term like 2ac. If 2ac equals 6a, and a equals a, then c must equal 3. So we're forming the perfect square open parenthesis, a plus 3, b plus 3, close parenthesis squared. When we expand this, we get a squared plus 9, b squared plus 9 plus 6, ab plus 18b plus 6a. Now we can identify the missing terms. Comparing our expansion with the original expression, the first missing term is 9, the second missing term is 6ab, and the third missing term is 18b. Let's verify our answer. If we substitute our missing terms, we get a squared plus 9b squared plus 9 plus 6, ab plus 18b plus 6a. This equals a plus 3b plus 3 squared, which confirms that our answer is correct. Now, let's move on to our second example. Again, we need to find the missing terms to make this a perfect square. For this problem, we'll again try to form a trinomial squared. We have x squared and 2x as terms. This suggests a pattern like x plus something squared. Let's try the pattern. X plus 1 over x plus 1 squared. When we expand this, we get x squared plus 1 over x squared plus 1 plus 2x over x plus 2x plus 2 over x. Let's simplify this expression. 2x over x simplifies to 2, so our expression becomes x squared plus 1 over x squared plus 1 plus 2x plus 2 over x. Now we can identify the missing terms in our second example. Comparing our expanded expression with the original one, the first missing term is 1 over x squared, the second missing term is 1, and the third missing term is 2 over x. Let's verify our answer for the second example. If we substitute our missing terms, we get x squared plus 1 over x squared plus 1 plus 2 over x plus 2x. This equals open parenthesis x plus 1 over x plus 1 close parenthesis squared, confirming that our answer is correct. Let's summarize what we've learned. When completing perfect square patterns, we identify the terms that suggest the form a plus b plus c squared. The key is to recognize the pattern in the given terms and figure out what a, b, and c should be. Welcome to this mathematics video where we'll solve a system of equations problem. We'll work through the solution step by step to find the value of a specific fraction. Let's look at our problem. We have real numbers a, b, and c that satisfy the following system of equations. 2a plus b plus c equals 0, and ab plus ac plus bc equals 0. We need to find the value of the fraction a squared plus 1 divided by b squared plus c squared plus 2. Let's start by analyzing the first equation. From the equation 2a plus b plus c equals 0, we can rewrite it as a plus b plus c equals negative a. Now, let's square both sides of this equation. We get the quantity a plus b plus c squared equals the quantity negative a squared. Next, we expand the left side of the equation. The square of a plus b plus c equals a squared plus b squared plus c squared plus 2, ab plus 2, ac plus 2bc. And on the right side, negative a squared is simply a squared. Now, let's use our second equation from the original problem. We know that ab plus ac plus bc equals 0. So, substituting this into our expanded equation, we get a squared plus b squared plus c squared plus 2 times 0 equals a squared. Simplifying this equation, we get a squared plus b squared plus c squared equals a squared, which means b squared plus c squared equals 0. Since b squared plus c squared equals 0, and both b squared and c squared are non-negative for real numbers, we can conclude that both b and c must be equal to 0. Now, let's go back to our first equation. If we substitute b equals 0 and c equals 0 into 2, a plus b plus c equals 0, we get 2a plus 0 equals 0, which means it equals 0 as well. Finally, let's calculate the value of the fraction we were asked to find. We need to find a squared plus 1 divided by b squared plus c squared plus 2. Substituting a equals 0, b equals 0, and c equals 0, we get 0 squared plus 1 divided by 0 squared plus 0 squared plus 2, which simplifies to 1 divided by 2, or 1/2. Therefore, the value of the fraction a squared plus 1 divided by b squared plus c squared plus 2 is equal to 1/2. Let's look at our problem. Given real numbers a, b, and c that satisfy the following relationships, a equals the fifth root of 5 minus the cube root of 3 minus 2. b equals 3 minus 2 times the fifth root of 5. And c equals the cube root of 3 plus the fifth root of 5 minus 1. We need to find the value of a squared plus b squared plus c squared, divided by a times b plus a times c plus b times c. Let's approach this step by step. Step 1. We'll first verify that a plus b plus c equals 0. Let's substitute the values and simplify. A plus b plus c equals the fifth root of 5 minus the cube root of 3 minus 2 plus 3 minus 2 times the fifth root of 5 plus the cube root of 3 plus the fifth root of 5 minus 1. Now let's group like terms. For the fifth root of 5 terms, we have the fifth root of 5 minus 2 times the fifth root of 5 plus the fifth root of 5, which equals 0. For the cube root of 3 terms, we have negative cube root of 3 plus cube root of 3, which equals 0. For the constant terms, we have negative 2 plus 3 minus 1, which equals 0. So, a plus b plus c equals 0 plus 0 plus 0, which is 0. This is a very important observation that will help us solve the problem. Step 2. Now, we'll use the square of some formula. Since we verified that a plus b plus c equals 0, we can use this fact with the square of some formula. We know that for any three numbers, the square of their sum equals the sum of their squares plus twice the sum of their products. So, a plus b plus c squared equals a squared plus b squared plus c squared plus 2 times a times b plus a times c plus b times c. Since a plus b plus c equals 0, the left side becomes 0 squared, which is 0. Therefore, 0 equals a squared plus b squared plus c squared plus 2 times a times b plus a times c plus b times c. Step 3. Now we'll solve for a squared plus b squared plus c squared. From the previous step, we have 0 equals a squared plus b squared plus c squared plus 2 times a times b plus a times c plus b times c. Rearranging to isolate a squared plus b squared plus c squared. A squared plus b squared plus c squared equals negative 2 times a times b plus a times c plus b times c. This is a crucial insight that directly relates to our target expression. Step 4. Now we'll compute the desired ratio. Recall that our target expression is a squared plus b squared plus c squared divided by a times b plus a times c plus b times c. We can substitute what we found for a squared plus b squared plus c squared. The ratio becomes negative 2 times a times b plus a times c plus b times c divided by a times b plus a times c plus b times c. Simplifying, we get negative 2 times a times b plus a times c plus b times c divided by a times b plus a times c plus b times c, which equals negative 2. Therefore, the value of our expression is negative 2. Let's summarize what we've learned in this problem. Welcome to this math video. Today, we're going to prove an interesting relationship between the sum of squares and the sum of fourth powers when the variables have a constraint. Let's look at our problem. We have a system where x, y, and z are non-zero numbers that satisfy the equation x plus y plus z equals 0. We need to prove that the square of the sum of squares, namely x squared plus y squared plus z squared, all squared, equals twice the sum of the fourth powers, which is 2 times the sum of x to the fourth plus y to the fourth plus z to the fourth. Let's start with our given equation and see where it leads us. Step 1. We'll begin by squaring both sides of the equation x plus y plus z equals 0. The left side becomes x plus y plus z quantity squared equals 0 squared, which is simply 0. But we also know that when we expand this square, we get a different form. By the binomial expansion, x plus y plus z squared equals x squared plus y squared plus z squared plus 2 times x y plus yz plus cx. Since this equals 0, we can write that x squared plus y squared plus z squared plus 2 times the quantity x, y plus yz plus cx equals 0. Rearranging to isolate the sum of squares, we get x squared plus y squared plus z squared equals negative 2 times the quantity x, y plus yz plus cx. This is a key insight that we'll use in the next steps. Step 2. Now, let's square both sides of the equation we just derived. On the left side, we get the square of x squared plus y squared plus z squared, which is exactly what appears in our target expression. On the right side, we get negative 2 times xy plus yz plus cx, all squared, which simplifies to 4 times xy plus yz plus cx squared. Therefore, we've established that the square of the sum of squares equals 4 times the square of the sum of products. So we have x squared plus y squared. Therefore, we've established that the square of the sum of squares equals 4 times the square of the sum of products. So we have x squared plus y squared plus z squared, all squared equals 4 times x y plus yz plus cx squared. Step 3. Now let's focus on expanding the expression x y plus yz plus cx squared. When we expand this, we get x squared y squared plus y squared z squared plus z squared, x squared plus 2 times xyz times the quantity x plus y plus z. But remember, our constraint tells us that x plus y plus z equals 0. So the term 2 times xyz times x plus y plus z becomes 2 times xyz times 0, which is 0. Therefore, xy plus yz plus cx squared simplifies to x squared y squared plus y squared z squared plus z squared x squared. Substituting this back into our equation from step 2, we get that x squared plus y squared plus z squared. Substituting this back into our equation from step 2, we get that x squared plus y squared plus z squared, all squared equals 4 times the quantity x squared y squared plus y squared z squared plus z squared x squared. Step 4. Now we need to find another way to express the square of the sum of squares. Let's expand x squared plus y squared plus z squared, all squared directly. By the binomial expansion, we get x to the fourth plus y to the fourth plus z to the fourth plus 2 times the cross terms, which are x squared y squared plus y squared z squared plus z squared x squared. Let's denote the sum of the cross product terms as s. That is, s equals x squared y squared plus y squared z squared plus z squared x squared. So we have two expressions for the square of the sum of squares. From the direct expansion, we have that it equals x to the fourth plus y to the fourth plus z to the fourth plus 2s. And from our earlier derivations for the square of the sum of squares, from the direct expansion, we have that it equals x to the fourth plus y to the fourth plus z to the fourth plus 2s. And from our earlier derivation, we know that it equals 4s. Since both expressions equal the same thing, we can set them equal to each other. So we have x to the fourth plus y to the fourth plus z to the fourth plus 2s equals 4s. Subtracting 2s from both sides, we get x to the fourth plus y to the fourth plus z to the fourth equals 2s. But we know that 4 south equals the square of the sum of squares, so 2s equals half of that. Therefore, x to the fourth plus y to the fourth plus z to the fourth equals 1/2 times the square of the sum of squares. Multiplying both sides by 2, we get our desired result. The square of the sum of squares equals 2 times the sum of the fourth powers. Let's summarize what we've proven. When x, y, and the sum of squares equals 2 times the sum of the fourth powers. Let's summarize what we've proven. When x, y, and z are non-zero numbers that sum to 0, then the square of the sum of their squares equals twice the sum of their fourth powers. This is a beautiful result that shows the elegant connections in mathematics between different types of power sums under constraints. As a challenge, try to extend this result to 4 variables or find similar identities for other constraints. Thank you for watching this proof. Remember that in mathematics, constraints often lead to beautiful and unexpected. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.